Hey math people, we are now looking at 7.9, which is linear programming practice. There are 3 problems in this, and we're going to walk through number 3 together. You guys are on your own for number 1 and 2. But number 3 has a couple of weird things, like literally a couple. There are 2 kind of weird lines that are going to crop up in this that do not exist in the other 2 problems. The other 2 problems are very much like the Desmos that you did earlier. So part 1, we're going to pull information out of this story problem. So I'm scanning the story problem for numbers, and I've discovered a total of hours for these cake decorators. So I want to get all of the cake decorating hours into a single equation. So we notice that there's specialty cakes, they take 2 hours, and these sheet cakes, they take 1 hour to decorate. And there's a total number of hours, so I'm just kind of noting all of these things, and let's give them some variables while we're at it. So a specialty cake gets to be X, the sheet cake is Y. And while we're doing this, because there's a graph on the page, it's never a bad idea to include these assignments on the graph. That way, if we refer back to the graph, we don't have to keep looking up which one was X, which one was Y. So we know that the specialty cakes get to be X, and this Y over here is the sheet cakes. That, because of the camera position, is I have to move the sheet around so that you can look at it. But we're going to put the sheet cakes up on the Y. And that way, if you just happen to glance at the graph, you will know what the X and the Y mean, because they're not just letters standing in for numbers now. They're specific. They mean something. All right, we're going to go looking for other things. And this is where some of the strange parts crop up. So Michael, who's in charge of this bakery, allows no more than 8 specialty cakes. That's a total. That means that 8 doesn't get the X. And then 16 sheet cakes. That 16 doesn't get the Y. Totals don't get the variables. These are separate individual numbers that I'll show you how to work in later. This isn't something you'll have to do on the other graphs. The other graphs are much more like the ones we've already practiced on. Okay, and finishing out our exploration of the story problem, we find the word profit, which is something that all business owners like to hear. They like the idea of profit. It keeps the business running. And we notice that there are $300 profit. That's a decent profit for these specialty cakes. And $70 for the sheet cake. So I'm going to star this profit equation because I'm going to need it later, but not right now. In the beginning of the business, you generally don't make a profit. Profits come at the very end. So we're going to worry about the other equations first. The profit equation comes at the very end. So I'm going back to these cake decorators, and we know that there's a 2X. We also happen to know that there's a single Y, and we know that we cannot go over those 20 hours. So we have a cake decorating hours rule or inequality. Here's where the weird things come in. The specialty cakes have a limit. That's the X. Okay? They have a limit of 8. So again, if you label everything as you go, you never forget who's what. So these specialty cakes, X cannot go over 8 in a week for whatever reason. Maybe there's something else going on in this shop and they don't have the time to spend on it. But X cannot go over 8 for a week. Okay, that's a total of just the X for a week. It doesn't have anything to do with the other group of cakes. They have their own limit. They are limited to 16 in a week. They don't take as much time as the specialty cakes, which are special by definition, but they still take time. So maybe it's materials. We don't know exactly why there's limits. We just know that there's limits on these. So there are the equations. And now we have equations out of the story problem, and we're ready to go on to part 2. Here we are in part 2. We've got a graph. This is where we're going to take the information, the constraints or limits that we got from the story, and we're going to graph them so we have a picture of what our business operation looks like, because sometimes it's a lot easier to work with a picture. We do, though, want y to be alone. So this first one, we're going to have to rearrange it a little bit because y is not alone. There's other things on that side. So we're going to separate off. We're going to subtract off all of the x terms. That includes the 2. 20 and minus 2x are not like terms. They don't combine. So on the left side, we still have that 1y. And on the right side, this is the easy part of math. We can't combine them, so we're basically just making a list of what's on that side, a 20 and a negative 2x. Now, if you need to get rid of a number that's attached to y, you divide it through everybody like this. You really don't have to do this with a 1 because it doesn't change anything, but this is what it would look like if it was some other number, like a 5 or a 2 or something like that. And the nice thing about dividing it is it does show you where the slope is, and it shows you that bottom number, if you don't have a fraction for a slope, it turns it into a 1. So we're going to start on the y's 20. Remember, if y is involved, you always start on the y. Don't start with your x. No one wants to start anything up with their x again. That's why it's an x. So if you have the option to avoid x, you avoid it. We're going to go down to over 1 on our slope. So there's our starting 20. Got our ruler ready. We're going to go down to over 1. And again, we want these to be really accurate. This is business, okay? So the more accurate you can make it, then the more predictable your profit, your income, your output, all of that. So you want this to be really accurate. So I'm repeating the slope as I go down the graph. And then we're going to relive our glory days of kindergarten. We're going to play connect the dots with a ruler because, it's more accurate. All right, we have a boundary on the graph. The constraint became a boundary that we cannot cross. Next up, we have an x. It is the only variable we see. And as much as we don't want to start anything with our x, that's the only variable we've got. So we come down here to the x and find the number we need. We need the 8. Okay, there is no y in this inequality. None. Which means we cannot touch the y-axis. If you can't touch a line, you're probably parallel to it. So we're going to come down. We're not going to touch that y. We're going to go parallel to it. And we're going to hit the x at the 8, which is basically what our rule or the inequality was describing. It was describing a line that hits the x-axis at the 8 and doesn't go near the y. So we've got another boundary on the graph. Last but not least, we've got our decorating hours, the specialty cakes. Here we go, the sheet cakes. Only a y, no x. We don't have to start with x at all. Y cannot go past 16, so it can't be up in the 17s and the 18s. Y has to be 16 or less for the week. So because y is the variable we've got, we're going to start on y with our 16. There's no x, none. And if you can't touch the x-axis because you don't have an x, then you got to be parallel. So we're going to make a parallel line. And these are the two lines, this horizontal through the y and the earlier vertical line through the x, that makes this graph a little bit different from the others. Problem number 2 does have a vertical and not a vertical, does have 3 different lines, but they're more like the cake decorating line, where there's an x, a y, and a total. So they're a little bit easier to pull out of the story. Okay, we are now going to make the feasible region. That's the region where the business actually operates. So we're going to come out from the origin, but the moment we hit one of these lines, that's the boundary. We can't go past it. The moment you go past it, you're past where the business can operate. You don't have enough hours, you don't have enough manpower, you don't have enough space, you don't have electricity, you don't have materials. It could be a number of things that, for whatever reason, your business won't work if it goes past those boundary lines. And what we're creating is we're creating a picture of the business. It's operating anywhere in here. We can operate our business. Okay, so now that we've got a picture of our business, we're going to go looking for places where we maximize and minimize. The origin is always a minimize spot. The other spots, at least if it's connected to the shape, there are a couple of graphs that are out in the middle of nowhere that don't have an origin, but most of ours, the origin is one of your points. So we're wandering around now and we're circling the vertices, the corners, okay, where the boundary lines cross other boundary lines, they change direction in the shape. So we have these vertices, and there's 5 of them. That's because we ourselves drew 3 lines on the graph. So we've got 5 different vertices. Okay? So on the last page of your worksheet, we're going to record what those vertices are. So I'm going to start with this guy. He's on the y-axis. That's the sheet cake axis. He's on the y-axis. So that's a 16 for the y, not the x. The x is actually 0. X is left and right, and that first point isn't anywhere left or right, so it's 0. But the next point over, he's 2 over. That's 2 for the x. But he's at the same height, and that's y. Y is a measure of how tall or how high something is on these 2-dimensional graphs. All right, next point. This guy, as far as left and right is concerned, he's at an 8 on the x, and his height is 4. So he is an 8 for the x and a 4 for the y. And if you need to put x, y on there to remind yourself, that's not a problem. If you don't, that's fine too. All right, this guy, he's down on the x at the 8, but he doesn't have any height. So that's a 0 for the y. And this 5th one, that's that origin. There it is, the origin point. He's part of the shaded region. He's on a boundary of the shaded region. He counts, but he's the lowest one, which means that he's a minimum. So we're actually not going to test him in a second. And we've cleared up the xy's. All right, we have our graph. We have information from the graph. We are good to proceed to the last phase. Last part, we have almost made it. Here we go. We got information out of the story problem. We have information in a picture on a graph. We are ready to figure out money making. Okay, in order to do that, we're going to go back to this profit equation. Okay, it's after the graph, after you find the vertices or the corners that you find the profit. Okay, so I'm going to record the profit equation. So the profit equation had 300 with the x, those were the specialty cakes, plus 70y, and that equals the profit. This is not an inequality like the others. This is, it equals money. We like money. Money makes us happy if we're a business owner. And what we're going to do with this profit equation is we're going to grab the vertices and plug in the x and the y into the x and into the y of the profit equation. We're going to leave out the 0 because that's the minimum. That's really not that important for our profit equation. We want to maximize it, not minimize it. If you were trying to save money for costs like buying water, buying sewage, buying leasing property, all of that, then you would want to minimize. Then you might consider the 0. We're not. So here comes our first test. We're putting 0 in for x, 16 in for y, and then we're just going to run an equation. Okay, so 0 plus 1120 gives us $1,120. That is not a bad week in business for this cake. Okay, next vertex, we're going to plug in the x and the y. And this one, I'm pretty sure is going to be bigger because we have 16 into that Y spot again, but now we have something contributing from the X spot. So this one's going to be up a little bit. We have 600 from that 300 times 2. And then we have that 1,120 repeating itself. And then we're going to add on, and now we've got more money. We like this vertex better, more of a profit. So I'm going to kind of X out the one above it because that one's just not making as much money. Okay, let's try our 8 and our 4. 8 will go in for X, 4 will go in for Y. Again, we're just basically repeating this profit equation over and over in each of the vertices. So here comes our X. Here's the Y. 300 times 8 gives us 2,400 or 2,400, and 70 times 4, that's 280. We add those together. All right, lots more money. Almost 1,000 more than the last group. Okay, so I like this one best of all. Okay, obviously the minimum, not caring. This one is probably going to be less because we have a repeat in the X. It's an 8 again, but the Y went down. The Y is down to 0. So there's nothing coming in from the Y. It's nothing. So we're going to get that 2,400, but then we're going to add nothing to it. So this is a no-brainer. That 2,680, that is our winning profit. So now we're going to remember that, oh hey, the X and the Y actually mean something. So we know an 8 and a 4 will get us the most profit, but 8 what? 4 what? We have to remember what those 8 and the 4 was, which is why on the other page we were marking off who was X and Y. So we could remember X was the specialty cake, and Y was the sheet cake. And for quick glances, we also put them on the graph. So you can look at the y-axis and the x-axis to see, yeah, I remember who was what. So 8, that's the specialty cake. That's going to help us make the most money. So we want to, in a single week, make 8 specialty cakes. And then we also want to make 4 of those sheet cakes. Those are just the flat cakes that maybe you pick up for a birthday. The specialty cakes, made to order, special order, something like that. And money, we are making $2,680 off of basically 12 different cakes, 8 specialty and 4 sheet cakes. And you have completed a full linear program. Congratulations.